the right hand side, then I'll have this one. So this we are very familiar with this wave equation. It's just one variable here, and this solution gives us two solutions. One is the e to the minus I kr, and the other one is e to the I plus I kr. Right? And then I can move this r over here, move this r over here. So what does these two terms mean? One is the outgoing and the other is the incoming, right? So now I have to assume that there's only outgoing wave but no incoming wave. And the reason I can assume that is it's called the so basically if I want to make this solution unique, I need to impose some condition here. And then I think the professor will later mention about this Sommerfeld radiation condition. Without that condition, then your solution won't be unique. But by adding that condition, we can assume that either the wave is exponentially growing or exponential decay. And in that case, then we can get rid of the incoming wave, assuming the wave is only going outward. Now we can get rid of this term here. So what's left is the coefficient b here. We don't know. And how to get this coefficient b? Remember, we haven't used this delta function yet. We are solving the problem at r, not at the origin. So now we have to deal with this delta function. So one common trick to deal with the delta function is to integrate, do infinitesimal integration around the delta source. And then I can make the right hand side equal to 1. And hopefully I can get rid of some of the terms on the left hand side by assuming the volume to be infinitesimal. Alright, so now what we can do is we integrate this over a delta v. When we make this small, so we know dV will just become 4 pi r squared dr, right? And this g goes with 1 over r. And this term is just a phase term, so it will still stay at 1. So now we can see that the whole term becomes r dr. And as this volume goes to 0, we can see this term actually will vanish. So now we can always make this smaller and small, and then we'll get rid of this term. So now this term is gone. You have -1. Okay. And then now we see this divergence again. This volume integral of the divergence. Then we can change it to a surface integral using the Gauss theorem. Alright. So what's the normal component of the gradient of G? In spherical coordinate. It's just a partial r, right? Everybody, do you see that? So now we can put in that b to the EIKR here. But keep in mind this b is going to 0, so the exponential term will just become 1 because the the distance is much smaller than the wavelengths of the wave. So the e to the IKR, it will just go to 1. So now I have, and this ds will just become, because it's a spherical symmetry, so we'll just multiply. So every point on the sphere is the same. So I can just simply multiply the area, the surface area of that volume. So integration ds will just become 4 pi r squared, right? And then the exponential becomes 1, and 1 over r derivative will give me b x minus r squared, right? So now we can see that b is just simply 1 over 4 pi. And then now we have the scalar Green's function. In free space. But keep in mind that we have, at the beginning we shift the origin from r prime to r, to 0, I mean. So if we add this, shift this back to r prime, because only the distance, relative distance between the r and r prime matters. So we can always shift this back to r prime. So this will just become e to the ik r minus r prime over 4 pi. Distance between r and r prime. And we can see the scalar Green's function doesn't depend on, only depends on the distance between these two, so we can also write this as g minus g prime. So now we have derived this the scalar Green's function. How do we find the output from a delta source, from any kind of source here? So how do we find this phi here from S? What we can do is first we expand this source in terms of delta function. And this we often do it in quantum mechanics as well. So we expand this in terms of a set of bases formed by the delta function. And the S r prime will just be the meaning of S r prime will be the spatial representation on that set of bases. So we can always expand it that way. So now what we can do is we do, so to make these two the same, we can multiply this equation by the SR prime and do the volume integral again. And the right hand side will just become the same, right? So what we can do is we do the volume integral of, say, this equation 2, and multiply by s prime. Sorry, this should be r prime. So integrate over r prime. And then we can just, by comparison, we can see this phi. It's just minus which is exactly the meaning of convolution here. So to get the output of the source, we just need to convolute this source with the system function, which is the Green's function. Now for our scalar free space scalar case. Okay, so now we can start with the vector Green's function. And so let's consider the homogeneous case first, because for inhomogeneous case, this Green's function may not be solvable analytically, so you may have to use some numerical methods. But if I can, if I assume this mu becomes homogeneous mu, and this epsilon becomes free space, become homogeneous epsilon. And now I can have vector wave equation like this. So now we do the use vector identity to break this into two terms. One is Laplacian of Okay, so now we are arranging the terms and have So we can replace this divergence of E by the charge density. So this becomes rho over epsilon. And then the rho is just the time derivative of the rho would just become the divergence of the current. That's the continuity equation, right? So we know that the time derivative of rho just become the incoming of the current density, right? So now I can replace everything by J.
Excuse me, on your left-hand side, why does the view
Where? Here?
So mu should be moved left of the curl, right?
Oh, so I have made an assumption here. I'm solving a free space vector Green's function. So this becomes a scalar. So I can take this out and multiply to here. And then the mu I'll just put in the k-square, and mu here I'll just multiply.
Oh yeah, sorry.
Okay. And
excuse me, about I omega real equals to minus divergence J, do you take divergence for both sides of the above equation?
No, this is the continuity equation. It means if in time domain is the change of the current density. It's just the incoming of the current, right?
Yeah.
So actually, I'm missing a minus sign here because I'm using keep in mind that we're using the e to the I minus I omega t convention. So this will have a minus sign here. So now this becomes gradient of divergence J over 1 omega epsilon. Minus 1 I omega. So using what we just derived for the scalar wave, scalar Green's function, we can find this the solution to E based on the source, right? We take this as a whole source. So E will just become an convolution between the source and the Green's function, right? With this whole source. Oh, sorry, I need a minus sign here. Because remember, we have a minus sign here. So this will be minus, this will be plus. So now, but this doesn't look exactly like what we want, because we want a current convoluted with some kind of Green's function. But now we see so many derivatives on this current. So we want to move these derivatives onto the scalar Green's function. the way of doing that is again using chain rule. And we can see there are two derivatives on this current mean, and we have to do at least twice chain rule. Okay, so so first we have to use identity here, which is but now we see some problem here because you can see G gradient, this thing will become this minus here. I can move the gradient to G. The problem is that here is a gradient. It's not a divergence. So when we integrate this over a volume, we cannot use the Gauss theorem. So here's the problem. So now we have to use a trick here. So we assume this scalar function, capital F, equals to G times small f, where small f is just divergence of the current. And this is a scalar function. And then we introduce a constant vector. So now we use another identity. So now we can change this gradient to some kind of divergence. And the good thing about assuming a constant vector is that this term will just go away, because it has no spatial dependence. So it will just give me this A dot gradient of F. So now I can just do the integration. On the left hand side, and using the Gauss theorem, it will just give me m dot A F. Right? And then the left hand side, the right hand side, will give me and this I can always take out this A, take this A outside of the integral. So this volume, this surface integral, I can make it go away by using a very large surface, and then we can assume that the source is finite. When the source is finite, I can always choose a volume that's larger than the source. And then this F contains the derivative, the divergence of J. And on that surface, this term will always go away. We can always choose this surface. So we can make this go away. So now we can, what we need to do is, if we can show that this equal to this one, then we can show that this gradient, the volume integral of this gradient goes away. So on what condition can I just get rid of this A and say that this equal to this?
A is arbitrary.
Right. Because I can always choose an arbitrary A. So I can say that this equal to this. And because this goes away, I can say this goes away.
Excuse me, when you choose A as a constant vector independent of the location, that means this loss is generality for something like plasmonics or some nanostructure. Because sometimes the polarization may change. Some are their location dependent.
Well, this is just something that I introduced to prove that this equal to this. I can always choose a different one as long as it's not spatially dependent. I can always choose this kind of constant vector, and then I can prove that. This is just for proving this term. This term is it doesn't have any physical meaning here. So, is that okay?
Okay, we can generate it.
So now I can prove this gradient goes away. So that means this term goes away, and then I can just simply move this derivative from f to g. So now the integral of So now I've moved one of the derivative here. What I need to do is to move the other one over here. So now I have to use another identity here, which is but if you're careful enough, you may find that here h is a scalar, right? But here I have a gradient of g, which is a vector. So a common way we can do that is that we can split this into three split into x and y and z components, and then each component is a scalar function. And then we do it for all x, y, z using this thing. And again, we can make this go away. But now I can just move this del operator onto the Green's function. So since these two have the opposite sign, so that term will just become integral of R prime. Then I have this minus sign over here and gradient of this J. So we can see that this is a gradient of gradient. This is what we call a diet. So if you're comfortable with a diet operation, you can also replace this H by a diet. So you can see that by a vector. So gradient operate on a vector will give you a diet, which is a tensor. And the tensor multiplied by a vector will give you back another tensor, a vector. So this whole thing will be a vector form, which is your E field is a vector. So if you're comfortable with a diet operation, you can always do that. If not, you can separate into 3 components, X, Y, Z components, and do it separately. So now we have moved both operators onto G. And the E field we can just write out like this. Where I have taken out the I omega mu, that becomes there's a negative sign here. And it will just become plus k squared. So now we can call this as the vector Green's function, or dyadic Green's function. Dyadic Green's function. So we can see this is actually a tensor. Tensor dot with your source, give you a vector, and do the inner product will generate the electromagnetic the E field. But some people may argue that we shouldn't call this a diet because a diet can be written as a tensor, but a tensor is not necessarily a diet. And the reason is that a diet should be 2 vectors put together. You also can call it an outer product. So imagine column vector multiplied by row vector. But not all tensor can be written as this form. It can be written as one AB plus BCD plus maybe EF. A tensor can be written at this form, but only when it's 2 vectors put together can it be called a diet. So somebody may argue that we should call this a tensor Green's function, but anyway, because we have added this this term here, so now we have arrived at this dyadic Green's function. One more trick to do is that we can see these are operating on R prime. But I don't want it to operate at R prime, I want this to operate on R. can see that because the scalar Green's function only depends on the relative distance between r and r prime. So I can show that using the chain rule, we can show that if I operate on x prime, it's just taking out of a negative sign. And then similarly, the gradient will just become minus gradient prime on G. And the double gradient will become the same as double gradient prime on G. So now we can show that the Green's function is just another property that you may want to know is whether this tensor is symmetric or